Algebra 1, Lesson 78, we are graphing rational functions. Now, we have looked at rational functions in the past and graphed them, but these times we're actually doing a few transformations on them because they have the form of y equals a divided by x minus b plus c. The b and the c parts of these are what's going to move them throughout the coordinate grid. Now we have a couple vocab terms. Remember that our rational function is a function that has a variable in the denominator, and we say it's undefined when that denominator equals 0. And we need to exclude a value if that denominator is going to equal 0, so that is our excluded value. Discontinuous function has a break or a jump in the graph, and lastly, asymptote is a boundary line that our function approaches but never touches or crosses. That's actually our excluded value in our rational function and our c value. Those will give us vertical and horizontal asymptotes. Let's first practice with finding some excluded values. So, first, whenever we look at a rational function like this, we want to factor it first. So, we look and see if there's anything to simplify by factoring. And in this first case, the numerator can't be factored, nothing in common, but the denominator, I could pull out a 5 and get 6 plus a left in the parentheses. Now, because 5 is a factor in the denominator, but not a factor in the numerator, it's actually been added to 1 after being multiplied to a, we cannot simplify those, just like we can't simplify the a's in here. So we actually just have to go ahead and find the excluded value for the denominator. You can use either the factored or unfactored form, but when we do it, we can say, if we can't see the excluded value right away, we can set it equal to 0 to figure out what would a have to equal in order to make this 0. We subtract 30 from each side, get 5a equals negative 30, so a would be negative 6 if it were an excluded value. And finding those excluded values, when we have these rational expressions, we say that a cannot equal negative 6. For the second one, y equals 4 over 6m. Well, in this case, 6m can't equal 0, so m must not equal 0. Alright, and then m plus 2, so m plus 2 equals 0, so m can't equal negative 2. That would be our excluded value. And lastly, doing that calculation, m cannot be 2. That would be our excluded value. Now, how this helps us is that when we have these discontinuous functions, we see graphs like this. So this is the graph of y equals negative 1 over x plus 4 plus 3. And when we look at those asymptotes, the horizontal and vertical dashed lines there, we see some connection to our equation. Especially when we look at the vertical asymptote, x equals negative 4. If we look at the denominator here, we say, well, negative 4 is just the excluded value. So my vertical our vertical asymptote must be our excluded value for x. Then we look at my second one, my horizontal asymptote, y equals 3, and we see, well, that's just my c value. Now, the reason that that plus 3 is basically an excluded value here is, well, let's change around this equation a little bit, and I'm going to subtract 3 from each side, so we push it to the other side. So y minus 3 is equal to negative 1 over x plus 4. Now, if I were to plug in y as 3, I would get 3 minus 3, or 0, equals negative 1 over x plus 4. Now, think about this with me and how this logically can't happen. If we take anything, whether it's negative 1, or 10, or 100, or a million, whatever that number is, and we start to divide it. And we start to divide it by bigger and bigger numbers, meaning we're getting smaller and smaller and smaller. We're cutting it into more and more pieces. Will we ever get to 0? And the answer is no. We will never get to 0. We will still have an amount. It'll just be super small. Think about taking a pizza and cutting it into 4 pieces. Then cutting it again into 8 pieces, 16, 32, and so on and so on. Each of those pieces is still there, but they're just getting smaller and smaller and smaller. The pizza just doesn't just go away. So we say that in this case, because y as 3 made it equal to 0 on that left side, we have to exclude it. And so when it's in our normal form of a over x minus b plus c, that plus c is our other excluded value for our horizontal asymptote. Alright, so just putting this in just slightly different terms, saying it again, the vertical asymptote happens at x equals b. That is my excluded value for x. And the horizontal asymptote happens at y equals c. That's what would make that left side if we were to change this formula around a little bit. So for example, if we had y equals 2 over x minus 8, well, we would say that in this case, telling what is a, b, and c, a is 2, b is 8, okay, this 8 right here, and c is 0. Now, when we talk about our vertical asymptote, in this case, 8 is our excluded value. That would make the denominator 0. And c is 0 because we're not actually adding anything here. We have a plus 0, so our horizontal asymptote is at y equals 0. Let's just practice some of these horizontal and vertical asymptotes for a second. So for the first one, we're not going to do the second one because it's actually just the same. For the first one, we say, all right, my vertical asymptote is when x is my excluded value. So x can't equal negative 10, so my line must be at x equals negative 10. That's where my dashed vertical line would be. And my horizontal line, well, that's my c value, so y is equal to 3. All right, second one here. Vertical asymptote is at x equals 1. That's my excluded value. Horizontal asymptote, well, we have a plus 0, so y must equal 0 for my horizontal asymptote. And yes, I would like you to describe all of this, whether it's vertical or horizontal, in the entire equation, because remember, these are lines. Although they're dashed, they are still lines that we need to have the full equation. All right, and last one, vertical asymptote is x equals negative 3. That's my excluded value. And my horizontal asymptote is when y is equal to negative 10. Alright, so if we are graphing using these asymptotes, these are our 4 steps that we will take to graph them. Okay, with any of these rational functions, this is what we can do. Number 1, we're going to identify the asymptotes and graph them using dashed lines. So in this equation, 1 over x minus 4 minus 2, we are going to say, well, the vertical asymptote is that excluded value at x equals 4. We're going to put those dashed lines vertically. And horizontal asymptote is at negative 2, that c value. So a horizontal asymptote at y equals negative 2. And then we're going to make a table of values. And I will encourage you to always use values on the left side and the right side of your vertical asymptote, meaning, let's say we take 3 of each. So that we have, okay, we'll plug in x as 1, 2, and 3. We're going to skip our vertical asymptote because it's just going to come up undefined. And then we're going to plot 5, 6, and 7. Plug those in and plot them. Okay? Now, how we do this, remember, I'm just plugging in my x value as 1 and simplifying. So, for example, if I plug in x as 1, I'm going to get 1 over 1 minus 4 and then minus 2, which means that I get a negative 1/3 minus 2, meaning I get a negative 2 1/3. So I go over and at my x equals 1, I go down negative 2 1/3. I'm going to be about right here. Then I do it again for 2. 1 over 2 minus 4 minus 2, which means that I get a negative 1/2 minus 2, so negative 2.5. Okay, it's going to be about right here. All right. And same for x as 3. So we have 1 over 3 minus 4 minus 2, and that ends up being negative 3. Okay, so we go down 3 goes to negative 3. We can start to see this curve, and the more points that we have, the better picture we will have of this curve, but that's about what it's going to look like. Now for the ones on the right side of my vertical asymptote, I'm going to plug in 5, and I get 1 over 5 minus 4 minus 2. which means I get 1 over 1 minus 2, so a negative 1. So at 5, I'm right here at negative 1. I'm going to extend this a little bit to have my 6 and 7. All right, I plug in 6, and I get 1 over 6 minus 4, so 1/2 minus 2. So I get a negative 1 and 1/2. All right, so 6 is at negative 1 and 1/2, so about right there. And my 7 is going to be about that right there. Okay, so you have your curve. All right, well, I'm going to show you a couple other examples of this that you can try on your own. All right, just remember these 4 steps. Find your asymptotes, graph them using dashed lines, and then make a table of values so that you can plot these. And remember that table of values, you're going to do some to the left and some to the right. Okay, here's a couple more that you can try. All right, lots of different ways that these can be used. All right, so let's look at this example as far as a real-life example of how we can do this. So the soccer administration plans to have 64 regular players on the team. Players will be divided equally among the coaches. There will be 1 backup player placed on each team. Number of players on each team, y, is given by the equation y equals 64 divided by x plus 1, where x is the number of coaches. So we need to determine the asymptotes, meaning what are the values for the number of coaches and the number of players that will not work in this situation. All right, so thinking about that, we would say my vertical asymptote of this rational function is my excluded value, so x can't equal 0, so x must be 0 for my vertical asymptote. And my horizontal asymptote, y, well, that's my c value of plus 1, so y equals 1, meaning that we can't have values. So if we have y number of players, so 1 player, that is not going to work out with how many, with any value of coaches. Whereas our number of coaches, we couldn't have x as 0, so 0 coaches, that wouldn't work for those 64 players. Okay? And then it asks if there are 4 coaches, how many players will each team have? All right, so if we plug in 4 as our coaches, that means that we're plugging in x as 4. So y equals 64 over 4 plus 1. So we end up with y is equal to 16 plus 1, so 17. All right, there must be 17 players on each team. All right, so here's one more example similar to that you can try on your own. But I hope this is helpful for your homework and for studying.